I have hinted to you in the previous class that the oscillations associated with the torsion of the shaft of a turbine generator system can be adversely affected by the behavior of the electrical network. That is, the electrical network under certain circumstances can destabilize the torsional oscillations. From a modeling perspective, shaft torsional transients are faster than the transients associated with say relative angle swings, low frequency swings and frequency stability phenomena, which we discussed some time back, or the voltage stability phenomena, which we discussed some time back. Therefore, the most important modeling difference is that for study of torsional transients and their interaction with the electrical network, one has to consider network transients and stator transients of a synchronous machine. Okay. Today's lecture, we will continue our modeling. Our effort in the previous class was directed towards trying to understand how electrical network with series compensation in the form of a fixed series capacitor what kind of characteristics it has. Okay. So, today's lecture we will try to complete that analysis, and the icing on the cake as far as the analysis is concerned is a startling phenomena, that is, when we have a series compensated network with a series capacitor, fixed series capacitor, you can actually cause shaft torsional oscillations to grow. We can cause shaft torsional oscillations to grow. This phenomena in fact is called sub-synchronous resonance. It will become clear in this lecture why it is called, why the word resonance is used. After all, we are talking of a transient phenomena, not kind of a forced response phenomena, but still you will understand why we use the word resonance under these situations. Okay. So, today's lecture we will complete our discussion on sub-synchronous resonance, and we will also, I will just give you a flavor of what we shall do in the next 3 or 4 2 or 3 lectures, that is the last part of the course on stability improvement. Okay. So, let us continue where we left off in the previous class. Just to recap, torsional transients require the modeling of multi-mass modeling. Remember that whenever we are studying torsional transients, the speed of all the turbines and the generator is not the same. Okay. Though in steady state they are the same, the transient differences in speed are usually caused by these oscillations, torsional oscillations. We consider network transients because, as we shall see, the interaction with the electrical network under certain circumstances is very important. Okay. But remember that we have to consider network and stator transients, but the frequencies involved are between say 10 hertz to around 50 hertz. So, often we can understand this phenomena using lumped models. Okay. So, this is why we left off last time. I just gave you a kind of a motivational example to show you that you can this particular system in fact displays the phenomena of shaft torsional oscillations. Okay. Then the frequency of course depends on the shaft stiffness and the mass of the generator and the turbine. Okay. Now, we will try to understand the interaction with the electrical network. I hinted to you last time that this problem arises often due to series compensation, that is, whenever you got a capacitor in the network, a fixed capacitor in the network, this electrical interaction becomes very prominent in the sense that there could be instability of these torsional oscillations. So, let us just study this phenomena, why it occurs, and take a case study. Now, remember of course, torsional natural oscillations, the natural oscillations of the shaft and mass and the shaft and turbine and generator system is effectively like a spring mass oscillation, but importantly the friction windage is very low, it is not much, the bearing friction etcetera is very low. So, the damping which we associate with these torsional oscillations is actually quite small. Now, electrical torque also affects the torsional oscillations. One can look at it as an input, though it is not strictly speaking an input, as we shall see. The damping due to electrical torque can be even negative. So, that is very important. Negative damping means that the oscillations can grow. Okay. So, this how this can occur is something we will try to understand in this lecture. So, before we try to understand the properties of an electrical network, in the previous class we in fact modeled a network. We shall just go through that again. Let us just take an example of a 6 mass system. Okay. 6 mass, there is a high pressure turbine, there is an intermediate pressure turbine. So, low pressure, there are 2 stages, LPA and LPB. There is a generator, there is a rotating excitation system, say a brushless excitation system, and the shaft sections which interconnect the HP and IP windings and various other turbines. So, sorry, not the windings, the turbines, the HP and IP turbine, the IP and LPA turbine, the LPA and LPB, and so on. Okay. So, they are connected, well rather I should say they are coupled via the shaft in this fashion. The HP is connected, coupled to the IP to the LPA, and so on. Okay. So, this is a typical data given in the IEEE first benchmark model, which is available in the literature. Now, how do you, for example, take out the frequencies? Just let us look at this turbine generator system in isolation. We say it is not connected to the electrical network. Okay. Let us assume that damping is 0. It is not 0, but it is a bit difficult to estimate and it is quite small. Okay. So, damping from purely mechanical sources is assumed to be 0. So, let us see what are the modal properties of this particular system. Okay. So, if I am going to try to analyze this system, remember what are the states? The states are the angular position of all the masses and the speeds of the masses. Okay. Remember that if you have got 2 masses connected by a shaft, this is something we did last time. You will have, suppose this is the HP turbine, this is the HP turbine and this is the intermediate pressure turbine of a steam turbine generator system. So, you will have dHP by dt is equal to, okay, this is the change of the angular position, okay. And if you look at in per unit, if you write this in per unit, it will look like this, is equal to THP. Okay. Remember, now we have got several turbine stages and the mechanical torque in fact is created in all these. Okay. So, for the HP turbine, the mechanical torque may be THP minus you do not have an electrical torque right at this mass, right, because this is a turbine. What instead you will write here is K times, the K is the shaft stiffness, delta HP minus delta IP. Okay. So, similarly, for the IP turbine, you will have 2 HIP by omega B d omega naught by dt. This is in per unit. Okay. So, T IP minus K times. So, this is K HP IP. Okay. So, this is K HP IP. So, it will be plus delta HP minus delta IP minus K IP LPA delta IP minus delta LPA. So, if the LPA turbine is connected here, then this is LPA and so on. Okay. So, the turbine equation, the equations of the masses, the motion of the turbine masses, in fact, d delta IP by dt is equal to omega IP minus omega naught. Okay. So, this K of course, is the shaft stiffness. Okay. So, the forces are, there is a driving force due to the mechanical torque created in the turbine, and if the shaft is slightly twisted, you also have a torque due to that. Okay. Twisted, I mean there is a torsion, okay, torsional force. So, you will have equations for all the turbine masses in this fashion, okay. And for, if you look at the generator itself, suppose this is the generator and this is the exciter, the equations are d delta by dt, delta, I will not use any subscript for generator, you will call it delta itself, okay, and d I am sorry, here in the previous thing it should be just omega, not omega naught. Okay. So, this should be omega h p and this should be omega I p. Yeah. So, d omega by dt, omega and delta are the speed of and angular position of the generator. Okay. In the previous class I had written a subscript g g, but for simplicity we will just not put any subscript. Okay. So, this will be 2 h generator, okay, by omega b. So, in this, for a generator, of course, there is no mechanism, the driving force actually comes from the shaft. Okay. In fact, so you will have minus of k delta minus delta exciter, okay, plus k times delta LPB, which is the shaft which is the mass connected here, the turbine, minus delta minus the electrical torque. Okay. For the time being, we will assume it to be 0. Actually, because the electrical torque is there is a coupling with the electrical system. Okay. So, this is the expression for the generator. Similarly, you can have an expression for the excitation system. So, our states eventually will be for a, you will have delta h p right up to delta x and omega h p right up to omega x. So, you will have actually for 6 mass system you will have 12 states. Okay. So, d by dt of this will be a matrix A into the states again delta h p to omega x. So, we can actually in isolation, if you take the turbine generator system, in fact, we can obtain the eigenvalues of A. So, find the eigenvalues of A. So, what we will do is first try to see that we do actually get an oscillatory kind of, you do get these torsional oscillations. We will just have a quick, we will run a Scilab program to really get this. So, what we will do is, yeah, I have already run it before. So, I will just show it to you again. Now, what you have is, you look at this program, eigenvalue mech sys, okay, dot sci. Okay, so open and yeah. Okay. So, if you look at this program, what I have done, it may not be absolutely visible on your screen. So, what I will just quickly also read through it. This is the data from the IEEE first benchmark model. We will assume omega is 2 pi into 60, it is a 60 hertz system, and the data corresponding to the turbine is given here. Okay. The H, the inertia constant value as well as the shaft constants. Okay. Now, I write this A matrix is very simple. Okay. So, I write this, the states are arranged of course, here as delta h p omega h p, delta I p omega I p and so on. Okay. So, of course, this is not required here, this part of the program. This is basically T m is equal to 1, T is equal to 1, and T m actually is made out of components. In a steam turbine with many turbine stages, the mechanical power actually is obtained as the sum of all the mechanical powers, okay, generated at the individual turbine. So, for example, the HP turbine could be 30% of the total mechanical power may be generated at the high pressure turbine, 30% at the IP turbine and 40% in the 2 LP turbine stages. Okay. So, anyway, this is not really important as far as our analysis is concerned, this particular analysis is concerned. You have got the A matrix, let us just take out its eigenvalue. So, we will do a limited analysis here. So, we will run this program, execute and form the A matrix. So, this is just forming the A matrix. mechanical system. This is the mechanical system in isolation, assuming that electrical torque is not is 0 or it's a constant. Okay. So, what you will find is, if you take out the eigenvalues are as follows. So, this is in radian per second, of course. So, if you look at this, there are basically 6 pairs of eigenvalues, 5 of them are torsional modes, oscillatory modes. You see this? Okay. So, if I in fact do spec A divided by 2 divided by 3.14, this is going to give you the frequency of these oscillations as well. So, this is the frequencies of the oscillations which will be seen. You see 2 zero eigenvalues, there are 2 zero eigenvalues because you have got an isolated system. Okay. There is absolutely isolated system and there is no friction. Okay. So, in fact, if you have got a completely isolated system, that is a spring mass system of this, or even if you take a isolated spring mass system, you will find 2 zero eigenvalues if we do not have friction. If you consider friction, then one of these eigenvalues, zero eigenvalues will disappear. Okay. So, remember that the zero eigenvalues are generally related to the motion, common motion, where all the masses move together. This is something we also did when we considered the analysis of a 2 machine system. So, things kind of keep popping out in different situations. Okay. The similar things keep popping out. So, if since you have no friction, you have 2 zero eigenvalues and both these eigenvalues are associated with the common motion. Okay. Now, in fact, this can be even inferred from the eigenvectors. Okay. So, if for example, if you look at, if you take out run this command. Okay. So, if you look at the eigenvector corresponding to the first eigenvalue, I am sorry. So, if you look at V colon 1. Okay. So, what you will notice is, remember that the states are arranged as delta H p omega H p, delta I p omega I p and so on. What you see is delta and omega, the terms which you get are of course, you will find an j, this is complex number, then this is a real number. This is, if this is a complex, this is a purely imaginary number, then this is a real number. That kind of behavior you see. This is not very surprising. Whenever you have got an oscillation, okay, and delta is the derivative of delta is omega, you know, it's proportional to omega. In that case, it's obvious that an oscillation if you have, then delta and omega will be 90 degrees phase shifted, and that is the reason why this delta eigenvector component corresponding to delta is 90 degrees to the eigenvector component corresponding to this the speed. Okay. So, this is why we have it. Also, you notice that different masses have different observability as far as this mode is concerned. For example, this mode will be hardly visible, or rather is not very well visible in the last 4 states, that is delta generator, delta omega generator, delta exciter and omega exciter. Okay. So, this is the property of this mode. Okay. Also, you notice that the delta component here is negative, while for the IP component it is positive. Okay. So, it means that you know, when one of the masses or rather the displacer, if one of the masses is going ahead, the other is going behind. Okay. So, there is a kind of a this is very common in any the mode shape in any kind of oscillatory mode. Okay. So, this is basically giving the nature or the relative movement of all the states, given that the first mode alone is excited. Okay. So, if you look at the second mode, you will have some other property and so on. Okay. Now, one thing of our interest of course is the zeroth mode. Okay. So, if you look at the zeroth mode, that is 1, 2, 3, 4, 5th mode, an interesting thing you notice is that this particular mode appears to be equally observable in all the states, all the deltas. Okay. So, this is as far as our analysis of the mechanical system taken alone, without worrying about the electrical system. If you just take the mechanical system in isolation, these are the eigenvalues. What about the electrical system? If you recall, in the previous lecture, we had gone through the modeling of the electrical system, which consists of the synchronous machine connected to a transmission line connected to, which is compensated by a fixed series capacitor. So, we will just quickly go through this. So, this is the synchronous generator model, but we did make some assumptions to make our analysis a bit simplified. Okay. So, the assumptions were, of course, that the line is represented by a lumped inductor. Okay. The second assumption we made was, we took E, the infinite bus voltage, as 1, and omega naught, the frequency of the infinite bus, as the rated speed. It was just a simplification. Okay. It need not always be so that the infinite bus to which this synchronous machine is connected to, its speed should be equal to the rated speed, okay, or its frequency is equal to the rated frequency. This is just a simplification we are doing for this analysis. It is likely to be very close to the rated frequency. Okay. If resistances are small, we can combine the flux and the current equations. Remember that there was a redundancy of states, because flux and currents are related by an algebraic equation. So, we do not have to separately write differential equations for the stator flux and the current. Okay. So, we combined those equations and made one equation. Okay. And if resistances are small, this can be easily done. Thereafter, we made another assumption that the rotor fluxes are assumed to be constant. Okay. So, we can define E1 and E2 in this fashion, and it is possible to substitute for psi in terms of I, okay, psi d and psi q in terms of id and iq, and get the first two equations. This is something we did in the previous class. So, I will not spend too much time on revising that again. Okay. We then converted these differential equations into the uppercase d and q variables. Okay. The advantage of doing that, of course, was the infinite bus voltages will become constant, okay, if I use this particular transformation of variables. Okay. Now, the capacitor equations were these in the ABC frame of reference. Okay. Then we converted them to the uppercase d and q variables. Remember, the uppercase d and q variables are obtained by using a transformation like Parkes transformation, but instead of theta we take a fixed omega naught t. Okay. Theta being the position, actual angular position of a synchronous machine. Now, if you combine all these equations, you get a state space equations of this form. Okay. So, you have got a linear state space equation. In fact, this A matrix is constant. Okay. But remember that these are the two sources, E1 and E1 dash and E2 dash are, remember, dependent on delta as well as the fluxes, the rotor fluxes, which for the simplified analysis we can assume to be constant. Okay. But one thing you notice here is that the electrical system is going to be affected by omega. There is an omega here, which is the speed of the generator, and E1 dash and E2 dash are also functions of delta, which is the rotor position of the synchronous generator. Okay. So, what you notice here is some kind of coupling. So, if you look at the mechanical system, okay, you are giving the torques, mechanical torques are kind of being generated at the various turbines. Okay. So, LPA, LPB, okay, and your electrical network. So, delta and omega of the generator affect the electrical variables, as we are seeing in these state space equations, and the electrical torque affects the mechanical equations. Is that okay? So, this is cumulatively gives you Tm. Okay. Remember that, so this is how really the interaction between the mechanical and the electrical system takes place. So, what we will do now in an isolated fashion, just like we did for the mechanical system, we will assume that delta and omega are constants and just see how what is the behavior of the electrical network, a simplified electrical network with all those assumptions we have made. What are the assumptions we have made? Resistances are small, okay, of the stator as well as the transmission line. Delta omega we will assume to be constant. Okay. Rotor fluxes are assumed to be constant. Okay. So, these are the assumptions we are making. So, we will just look at the properties of a electrical network which is connected to electrical network which connects the synchronous generator to an infinite bus. Okay. So, we will just write a simple program to obtain the eigenvalues of this A matrix, simple. Okay. If you look at this A matrix, what you will notice of course here is there is a kind of nice symmetry, well it is not a symmetry really, there is a kind of skew symmetry, Okay. So, what you notice here is minus omega b, here there is a minus omega b, here there is omega b, this is omega by b c, here you will have minus omega by x plus x double dash, this should be minus here, there is a small error, please note it, there is a minus sign here for this element 2 4. Okay. So, there should be a negative sign here. Okay. So, if you look at this is the A matrix or the state matrix corresponding to an electrical network looked at in isolation. Okay. Actually, there is a coupling with the mechanical system which occurs because of these terms. Okay. So, if we just run a simple Scilab program to obtain the eigenvalues of this system. So, if I have already programmed it, so I will just directly run it. So, what we need to do is of course execute a simple program in which I have for certain values of parameters I have taken out. So, if you look at this, it will turn out to be so, if you take out the eigenvalues of a compensated system, what you get is of course, it is a 4 by 4 matrix. So, you will get a set of eigenvalues. Okay. Of course, if you ought to really see the program because I have not told you what the values are, you know what the total x of the system and what the x the BC etcetera is. Okay. So, I will just open this. Open a file, yeah. So, the electrical system. If you look at the electrical system, this XL is what I will be using is XL is the total x plus x dash, x double dash plus any other reactance which may come in this series path. Its value is 0.7 and XC or rather what I have just forgotten what this capital XC. Okay. So, its XC is 0.3. So, if you look at the compensation level, it is 0.3 divided by 0.7. Okay. So, this is the percentage of compensation which is used. Now, the point is that the eigenvalues of the system are these. Okay. Now, what you notice is that there are two modes, there are two oscillatory modes in fact. You will find that this is 623, this is an imaginary, I is an imaginary number, purely imaginary number square root of -1. So, this is effectively a complex pair and this is a complex pair. There is no resistance considered. So, you get no real component. Okay. Now, these complex conjugate eigenvalues are in fact super synchronous in the sense that the frequency of these is greater than 60 hertz. Okay. So, one of the frequencies is coming out to be greater than 50 hertz and the other one is coming less than 60 hertz, sorry 60 hertz is the frequency used in this example. So, you have got two frequencies, one is super synchronous, one is sub-synchronous. Okay. Now, if you look at these modes carefully, one of the modes is 60, if you look at 20 is nothing but 60 minus 40. Okay. and 99 is roughly 99.27 is roughly 60, this is roughly 20.72, this is 60 plus 40. So, it appears that the eigenvalues are appearing in a certain form. Okay. So, you have got 60 plus some eigenvalue, some frequency, and 60 minus some frequency. This is very typical. Why is it typical? If you take a system like this, suppose this is a one phase of a three phase line, if the eigenvalues of this system, let us say r is equal to 0. So, you have just L and you have got C. Okay. If you just take this single phase in isolation, okay, then write down the equations in the A, B, C, A variables. Okay. You will find that obviously there is going to be an oscillatory eigenvalue which has got a frequency 1 by root L C. Okay. Now, this is in the phase domain. If I convert a three phase network of this kind, a balanced three phase network of this kind with r is equal to 0, of course, this r is equal to 0 is not important in this, it is true even if r is not equal to 0. The point is that if I take this, write the differential equations for a linear network and get an eigenvalue lambda for the A phase and similarly for the B and C phases. An interesting thing is that whenever we reformulate these equations in the dq variables, okay, then your eigenvalues will be plus minus j omega b. That is an interesting thing. Okay. So, remember that for example, in this network you have got XL is equal to 0.7 okay, in each phase and XC is equal to 0.3. Okay. So, if you look at XC is nothing but 1 by BC. So, BC is equal to 1 by 0.3. Okay. Now, if you look at just this phase in isolation, if you had just written the equations of this phase, the differential equations of one phase in isolation, you would have said that the frequency, natural frequency of this is 1 by root L C. So, this should be, this is equivalent to having omega b into L into B C is you can say C is nothing but, what we will do is just multiply omega b in the denominator. So, you will get this. So, this is nothing but equal to omega b divided by root of x L into B C. So, this is what we get as the natural frequency. Okay. Now, of course, if x L is given in per unit, so x L actual is nothing but x L in per unit into Z base and B C in per unit is equal B C actual value is B C per unit into Y base. Okay. Now, Y and Z base are related like this. Okay. So, it is obvious that the natural frequency will be the same whether you express x L and B C in per unit or in actual values. Okay. So, this is the expression of the natural frequency of an electrical network considered in isolation. Okay. So, if you look at this particular equation for these the values which we discussed here, what we will get is omega n is equal to omega b divided by root of 0.7 into 1 upon 0.3. Okay. So, that becomes omega b into 0.3 by 0.7. Okay. So, if you look at, if you just compute this, omega b is nothing but around 377 for 60 hertz. So, omega b into square root of 0.7 0.3 divided by 0.7. So, the frequency comes up the radian frequency comes out to be 246. Okay. So, as I mentioned some time back, the dq in the dq reference frame, if you formulate your equations and compute the eigenvalues, okay, then your eigenvalues will be, suppose in the ABC or each phase taken individually, you got an eigenvalue of lambda, in the dq you will get omega b. So, if your eigenvalues in the ABC turn out to be plus or minus omega n, what you will have is j omega n plus or minus j omega b. So, if for minus omega n, you will have omega n plus or minus j omega b. So, you will get 4 eigenvalues like this, okay, in the DQ reference frame. Okay. The 0 sequence of course is neglected with the assumption that everything we are considering here is balanced. Okay. So, what are the, so if you look at 246 radian per second, which is appearing on the screen, and actually take out its frequency. So, this is divided by 2 divided by 3.14, this is the Hertz frequency, it is 39.27. So, does that explain this? It is not 40 exactly, it is 39.27. Okay. So, the 4 eigenvalues which we got by doing this analysis in the DQ reference frame is in fact are in fact these eigenvalues. Okay. So, remember that you get these kind of complex pairs of eigenvalues. Okay. So, if you have got a series compensated network, you do get these oscillatory eigenvalues, and interestingly some of them are subsynchronous. Okay. So, the point now is you have got an electrical network which is series compensated, it has got oscillatory eigenvalues or oscillatory response, and the mechanical system also has an oscillatory response, so delta and omega T. Okay. Now, you can put all, say we had considered these systems in isolation, the electrical and the mechanical system in isolation, and said that here you have an oscillatory response. This in case you have got a series capacitor, then you have got an oscillatory response with subsynchronous and supersynchronous components. Okay. So, the thing is when you put these together, what is the eigenvalues of the system? Okay. It becomes a coupled system. Remember that delta and omega affect the electrical system. If you recall, if you look at our final equations here, the electrical system is affected by omega and the mechanical system is affected by the electrical torque. Okay. Electrical torque of course is equal to psi d I q minus psi q I d. Okay. So, we can actually compute this from the electrical states I d and I q. Okay. And of course, they will be also dependent on delta, because here it is this I d and I q are lower case. Okay. So, you will have a dependence on delta as well. So, in fact, the point is there is a, of course, this equation is non-linear. Okay. There are product terms. Remember, psi d is related to psi d is related to I d and psi q is related to I q. Okay. So, this is a non-linear relationship. This relationship is not linear. T is dependent non-linearly dependent on the terms of the electrical system, the synchronous generator and the electrical network, and the electrical network also is in a non-linear way related, because this comes out to be a product term. E1 dash will be a function of delta and omega is also a mechanical variable. So, this kind of non-linear relationship exists. What you need to do is, which we will not of course pursue here, is compute or rather compute the eigenvalues, linearized system eigenvalues. Okay. So, what you need to do is the mechanical system, you will have the delta and omega variable. So, I will call them x m is equal to a m into delta x m plus delta t. In fact, you will have minus delta t, that is okay. Well, it's not going to t is not going to affect all the states directly. If you recall, it will affect the generator states directly. So, you actually have to have a B matrix into delta T e, okay, and delta T e itself is equal to psi d 0 delta I q minus delta psi d into I q 0 minus psi q 0 delta I d minus delta psi q I d 0. Okay. So, this is the coupling thing. Similarly, you have got the electrical network equations. okay, electrical delta x c. This you have to do a linearization. This A matrix of course is linear, you do not have to bother. The nonlinearity comes here because this is a nonlinear, this is how you have to linearize this delta T e, okay, plus, okay, plus B e into delta omega and delta delta. Delta delta and delta omega are in fact related to x c. So, they are some matrix C into x n. Okay. So, I will call this also as some kind of C e into delta x e, and this is C into x n. Okay. So, you have to couple these two equations, okay, and get one grand state matrix, you will get it. Okay. So, I will not work this all out. So, you will get one grand state matrix of this kind. Okay. We will assume delta all the inputs delta I p, h p, delta the mechanical inputs are constants. Okay. So, mechanical power torque inputs to all the turbines will assume to be are constant, and also the infinite bus voltage will assume to be a constant. So, this is how you will formulate your equations. What I have written here is absolutely general. You can remove all the assumptions which we have, you can relax all the assumptions which we have made so far relating to the resistance of transmission line, the rotor fluxes, x d double dash not being equal to x d dash, x d double dash, x q double, sorry, x q double dash not being equal to x d double dash. So, all these assumptions can be relaxed, and this can be an absolute detailed model. Okay. You need not take the simplified model which I had discussed some time back, which the fourth order model, okay, that assumed that the rotor fluxes were constant, resistances were small and so on. Okay. You can relax all those assumptions. Now, one small thing which I probably a bit out of place, but I missed telling you is that there is nothing in this particular rule which I gave you relating the eigenvalues when equations are formulated in ABC reference frame and the DQ reference frame. Remember, there is nothing special about this being purely complex. Okay. So, if this is sigma plus j omega n, this will be sigma plus my, so this sigma will appear here also. Okay. So, there is nothing special about this being purely imaginary. This kind of relationship holds true even this is a complex number with a real part, it will also appear here. Okay. So, this is something which I forgot to tell you. Anyway, so we can actually using more detailed models put all these things together. Now, the point which is very important is that when I said that the electrical and mechanical system interact with each other, what happens? Well, you can actually do the eigenvalue analysis of the mechanical and electrical system put together, something what we did here, put them together, okay, and just do the eigenvalue analysis. But even before we do that, let us try to have some kind of insight into what will kind of happen in case the mechanical oscillatory frequency becomes close to or equal to the oscillatory frequency of the electrical network. Let us look at it in a cause and effect manner. Okay. So, this is called also called a damping torque kind of analysis. Assume that the mechanical system is oscillating at a fixed frequency, undamped oscillation is there, suppose, of the mechanical system. Let us say it is oscillating at a frequency omega, this omega. Okay. So, because of that delta, if this oscillation omega is observable in delta and omega, then the electrical network, this is like a input to the electrical system. Okay. Let us assume that the systems are kind of decoupled. Okay. So, this is a kind of input to the electrical system. The electrical system will respond, and you will find that in delta T also you will find this oscillation of sigma. Now, if this delta T e, the oscillation which is created is such that it actually enhances the oscillation which is already there. For example, if delta T e, if for example, omega of the generator is oscillating at a frequency omega, this is the frequency of oscillation of the generator speed around the equilibrium value, then it so turns out that the electrical network, okay, has a torque, electrical torque which is created like this. Okay. So, electrical torque is like this. So, electrical torque is in some way, if you look at these two waveforms, is some way proportional to minus of omega, you know. So, if suppose this is true. So, you know what this looks like? This is a kind of a situation where the mechanical system is getting an electrical torque, okay, which is proportional to negative of the speed of the generator. The things are exactly in, you know, out of phase. In such a situation, what will happen is that the electrical torque, okay, will enhance the oscillation. It is almost like having negative friction, viscous friction, and the oscillation will increase. Okay. So, this is a kind of a cause and effect non-rigorous reasoning, why sometimes it is possible that the electrical network can cause electrical torques which enhance the oscillation which initially caused this electrical torque variation in the first place. Okay. So, this kind of cause and effect analysis can reveal that we have got a potential problem. Now, one of the important things which you should note is that this need not be true, okay, but it turns out that for a series compensated network, that is for a network compensated by a capacitor, a fixed series capacitor, if the frequency here sigma, this frequency of mechanical oscillation is subsynchronous, then this kind of situation is likely to occur. Okay. And if that occurs, one can expect that there can be some problem. Okay. Now, I hope you kind of get the reason why. Another thing is why we can have a problem, potential problem. Okay. This problem will be very much enhanced in case this frequency is equal to the frequency of this in the DQ frame of reference. Okay. So, if the frequency of omega delta and omega, the torsional oscillation frequency is equal to or very nearly equal to the oscillatory frequency of the network, where the network is kind of modeled in the DQ reference frame, then this T can be very large or rather very significantly large, and this problem can really become very, very significant. Okay. So, the electrical torque may really cause a very adverse reaction, and the oscillation, this oscillation may start growing with time. Okay. That is why this thing is called sub-synchronous resonance. It's sub-synchronous because the electrical torque is found to have this kind of or near this kind of phase relationship, or rather it has got a significant component of this kind. It could be like this also. Okay. So, it has got a significant component of this kind in case this frequency is sub-synchronous, okay, and the network frequency comes close to this. Okay. Then you can show that the electrical torque has got a fairly large component which is proportional to, or which is kind of looks almost is out of phase with the electrical speed. Okay. So, this is a kind of cause and effect reasoning. If you feel uncomfortable about this kind of reasoning, no harm, you can actually do the eigenvalue analysis and see that this actually occurs. Okay. So, let us take a case study and end this lecture. So, if you look at this particular, we will take this example of a 6 mass system. If I compensate this network by 55% series compensation, there is one oscillatory mode which goes unstable. This is what we find by simulating the system. Remember, if you want to simulate this phenomena, you have to use EMTP like programs in which stator transients and network transients are not neglected. Okay. So, if you look at the expanded view, you can see that this oscillation has got 1, 2, 3, 4, 5, okay. Around 5 complete cycles in 0.2 seconds. Okay. 5 complete cycles in 0.2 seconds would mean around 25 hertz. Okay. 25 hertz would correspond to a frequency of roughly 160 radian per second. So, the thing is that if you look at this eigenvalue analysis, you do see this is also predicted by small signal analysis. Okay. By doing a small signal analysis, we can actually correlate what happens in simulation. You see that the subsynchronous network mode, if its frequency becomes close to one of the torsional modes, we had evaluated the torsional mode some time back. Remember, the torsional mode frequencies have hardly changed, okay? But the important thing is that the torsional mode damping has become negative, that is, the real part of this eigenvalue has become positive, and this happens because the coupled electrical network has got an eigenvalue or has got a natural frequency in the DQ reference frame formulation, which is absolutely close to this. So, whenever a network frequency comes close to this, the torsional mode becomes unstable if it is subsynchronous. Okay. Now, one important thing of course, which I missed telling you is that how much effect the electrical torque has on each individual mode depends on the controllability of a mechanical system mode by the electrical torque. In fact, in this particular system, the torsional mode 5 is hardly affected by the connection or the coupling to the electrical network. It shows that this mode is practically uncontrollable by anything you do in the electrical network. Okay. This is something you can actually analyze by looking at the eigenvectors of the mechanical system. In fact, if you look at the eigenvectors of this corresponding to this particular mode, both the right and left eigenvectors, they will have very small components corresponding to the generator mass. Okay. So, delta and omega components, that is delta of the synchronous generator and omega of the synchronous generator, the eigenvector vector components corresponding to these two states are generally very small, both the right eigenvector as well as the left eigenvector. Okay. That indicates that this fifth mode is not very well controllable by anything you do on the electrical network, and this is what is actually seen in this eigenvalue analysis as well. So, this is what happens in case for a subsynchronous torsional mode, there is a matched kind of frequency in the electrical network as well. This electrical network is subsynchronous because of the fact that the natural frequency, there is a oscillatory natural frequency of the electrical network because of the series capacitor. Okay. I have not shown the super synchronous network mode or the other modes of the system. I have just shown you only the torsional modes, the subsynchronous network mode, and very importantly the common mode. The common mode of this system is given here. It is the low frequency mode which you have already studied before. Okay. If you recall what I said last time, you do not have to unlearn what we did as far as the low frequency swing oscillations of 1 hertz were concerned. Remember that when we had done a study of a 2 machine system, we had considered the whole turbine mass system as 1, okay, and therein we had seen that there is a low frequency oscillation of around 1 to 2 hertz. Okay. Now, what we have done is we have represented the turbine generator system as a multi-mass model. Therefore, you are getting all these torsional frequencies, but this particular mode in which all the masses of the mechanical system move together still persists and basically is manifest when you couple it to the electrical system as this common mode or swing mode. Okay. So, the 0 eigenvalues which we saw in the mechanical system, which is isolated from the electrical network, now transforms itself into this oscillatory mode, the low frequency swing mode. Okay. Now, this mode is of course seen in this simulation. You see this low frequency mode as well. Okay. This simulation incidentally has been done for a step change in torque, a very small step given in the mechanical torque. This is the disturbance which is given, okay, of one of the turbines. So, please remember, just to summarize this particular phenomena, you can have adverse torsional interactions at subsynchronous frequencies due to a series compensated network. This is basically the crux or the important thing which you should take back with you after this lecture. I thought I would be able to start on improving stability methods in this particular lecture. At least I would kind of give you an introduction to that. We couldn't do that, we will do it in the next class.